Welcome to FE Exam Prep for Mechanical Engineers. Today we will review the voltage divider equation, which pertains to the electricity and magnetism section of the exam. Starting with a review, resistors are electrical components that dissipate energy by resisting current. They are represented by the squiggly symbol here. And if this is node 1 and this is node 2, and this is the current here, we know that voltage is going to drop across a resistor. So the voltage at point 1 is going to be greater than the voltage at point 2. And when you're working with a resistor, you're also going to want to reference Ohm's law, which states that voltage is equal to current times resistance. The next thing you're going to need to know is Kirchhoff's voltage law, which states that the sum of voltage changes within a closed loop must be 0. So for any given circuit, you might have a voltage source, a resistor, capacitor, maybe even an inductor. As long as that loop is closed, the sum of the voltage in is going to be equal to the sum of the voltage out. And then finally for this video, we'll be focusing on the voltage divider equation, which calculates the specific voltage drop across 2 points in a closed loop based off of the input voltage and resistances. When you're typically using this equation, you're going to solve for V out, so that's going to be the unknown, typically. Everything else here on the right is provided. When you're talking about R equivalent, the equivalent resistance of the circuit, you're going to be looking at the entire circuit. And when you're looking at Rx, you're going to be looking at a specific section of the circuit. And this will become more clear with an example problem. So here we have a simple circuit where we're asked to solve for the equivalent resistance, the current supplied by the source, and V out. Starting with step A, we're looking for the equivalent resistance of the circuit. We know that for resistors in series, the equivalent resistance is going to be the sum. There's a general equation to Rn. Applying that to this specific circuit here, the equivalent resistance is going to be 5 ohms plus 3 ohms plus 6 ohms. With some simple math in your head, that is equivalent to 14 ohms. Next, we'll move on to part B, solving for current supplied by the source. Oops. Okay. We'll start with Kirchhoff's voltage law. So for this closed loop, the voltage in must be equal to the voltage out. So the voltage from node 1 to 2 minus the voltage from 2 to 3, because remember voltage drops across a resistor, minus voltage 3, 4, and minus the voltage from node 4 to node 1 is going to be equal to 0. Then we'll apply Ohm's law. So the voltage from 1 to 2 minus the current 2 to 3, resistance from node 2 to 3, and so on. All equal to 0. Now, a resistor does not change the current throughout this circuit. So therefore we can simplify this equation, say that the current from 2, 3 equal to the same current going through resistor 2 and equal to the same current that's going through resistor 4. We can use that to be I. Taking this equation right over here, we simplify that the voltage from 1 to 2 minus that current, and then R23 is the same as R1, R34 is the same as R2, and R41 is the same as R3. It's going to be equal to 0. And you'll notice that this equation right here is the same as this equation right here. Then we'll solve for current. Which becomes 15 over 14 amps. So there's our solution to part B. Now we'll go on to part C, where we're solving for V out. And I kept two important numbers that we'll need for this equation, which is the equivalent resistance of the circuit and then the current throughout. So here we can say that V out is the same thing as the voltage drop from V4 to 1. And we know from Ohm's law that this is going to be the current times the resistor, which is the third resistor. Plugging in, we have V out is going to be 15 over 14 times R3, which is 6. When you plug that into your calculator, you get 6.43 volts. It's also important here to recognize that this 14 here is the same as this 14 here. And this is R equivalent. The 6 here is Rx. And the 15 here is V in. So without explicitly using the voltage divider equation, we were able to work it out with Kirchhoff's voltage law and Ohm's law. So now that we've kind of proved the voltage divider equation, let's try and use it in one more problem. Here we want to solve from the voltage drop from node 2 to node 4, which means V out is effectively V24. So then the Rx is going to be the equivalent resistance from node 2 to node 4. The denominator is always the equivalent resistance of the circuit. And then we have Vn. Okay, so we know that Vn is going to be 50 volts. Let's start by solving for R equivalent. So for resistors in parallel, equivalent resistance looks like this. Oops. Applying that to this specific problem, R from 2 to 3 is going to be 1 over 8 plus 1 over 10, and the inverse of that. Simplifying this, you get 40 over 9. And now the equivalent circuit, you can kind of just sum all the other resistances because now they're in series. So R equivalent is going to be equal to R1 plus R23 plus R4. which is equal to 5 plus 40 over 9 plus 2. Plugging that in, you get, in fractions, you get 103 over 9. So that's one of the terms we need. And then R24 is going to be equal to R23 plus R34, which is 40 over 9. R34 is the same thing as R4, so that's 2. Then you get R24 is 58 over 9. Now if we plug those in, I'll do this in green. The voltage from node 2 to 4 is going to be equal to 58 over 9 divided by 103 over 9 multiplied by Vn, which was provided as 50. When you plug that into your calculator, you get the voltage from node 2 to 4 is 28.16 volts. If I do a quick sanity check, I know that there's 50 volts coming into the circuit, so that means that no more than 50 volts could be leaving the circuit, and so I think that this answer could be correct, and then that's what I would select for the exam.